This video is going to be on differentiability and continuity. So we're going to look now at an alternative limit form of a derivative, and it's a lot of times useful in investigating the relationship between differentiability and continuity. So we're going to now change our definition of a derivative to say, instead of delta x approaching 0, we're going to say as x approaches c of f of x minus f of c over x minus c. Because once again, we're just looking at 2 points as x gets closer and closer to c, right? As x gets closer and closer to c, we're talking about the slope y2 minus y1, x2 minus x1, getting closer and closer to that tangent line. So it's still just y2 minus y1 over x2 minus x1. Now, note that the existence of the limit is in this alternative form requires that the one-sided limits both exist and that they're both equal. Right? If the limit doesn't exist, then this doesn't work anymore. So now we're going to call these one-sided limits in this form the derivative from the left and from the right. Now it follows that f is differentiable on the closed interval if it's differentiable on the open interval when the derivative from the right and the derivative from the left both exist. Now they don't have to be the same because we're talking about on different ends, but they do have to exist. Now when a function is not continuous at x equals c, that means it's not differentiable at x equals c. An example of this is going to be what's called the greatest integer function. And it's drawn like this with these kind of double barred brackets. Now, for those that don't know what a greatest integer function is, it basically takes any value and rounds it up. So we're talking about no matter what it is, if it's a decimal, if it's not an integer, it's going to round it up to the nearest integer. So 1 would be 1, right? It's going to round it down. I don't know why it said that. It's the greatest integer that's part of it. So if we're talking about 1.35, the greatest integer is 1 because that's what it's talking about. That's the biggest, that's the integer portion. So we're talking about the integer associated with whatever value it is. So 1 automatically is 1, and then anything that starts with a 1 is also 1. 2 jumps up to 2, and then anything with a 2 at the beginning also is 2. Same thing with negatives, right? Negative 2 is negative 2, but now we're talking about anything with a negative 1 is negative 2 because it's the lower version, okay? So when we go down, we're always going to be looking at 1 less than whatever we've got. So if we've got negative 1.3, that's actually negative 2. Now, notice that there are discontinuities at every integer, right? There's a discontinuity here, a discontinuity here, here, here. That means that it is not differentiable at any of those locations. And you can verify this by doing the derivative that we just talked about, f of x minus f of 0 over x minus 0. So if we take the limit as x approaches 0 from the left, we get the greatest integer divided by 0. So we know that as we approach 0 from the left, we're talking about negative 1, right? That's where it's approaching, negative 1. So this gives us negative 1 minus 0 over 0. And we know that that's going to give us infinity. Because if we're talking about, if you've got negative 1 over x as x approaches 0 from the left, that means that x is going to be a negative number. A negative divided by negative is going to give us that positive. So we're talking about 1 over 0, but we're talking about a positive number, so we're talking about infinity. Now, if we come from the right, we can see that it's approaching 0. So we know that that's going to be 0. 0 minus 0 is 0 over 0. Doesn't do us any good, right? But if I get really close to x on the positive side, I get a positive number, and 0 divided by any positive number is just 0. Now, it is true that differentiability implies continuity, but the converse of that is not true, okay? It's possible to have a function that's continuous, but not differentiable. Don't believe me? All right, let's look at example 3. The function f of x equals the absolute value of x minus 2, and we want to talk about what happens at x equals 2. It's not differentiable at x equals 2 because the derivatives from the left and from the right aren't equal. Now, how do you know that? Well, I know the slope over here is -1, the slope over here is +1. I could just eyeball that as a mathematician and know that. But can we prove it mathematically, where we don't have to just look and try to figure out from the graph? Well, let's look at those one-sided limits, right? So f of x equals the absolute value of x minus 2, right? So we're talking about the absolute value, the limit as x approaches 2 from the left of the absolute value of x minus 2 minus, if I plug in 2, I get 0, over x minus 2. That's just the limit as x approaches 2 from the left of the absolute value of x minus 2 over x minus 2. Since we're talking about from the left, we've got 1.999 or whatever, so we'll just use 1. 1 minus 2 is a negative number. A positive number divided by a negative number gives us negative infinity, right? No, it doesn't. It gives us -1. Come on, y'all. I didn't give you a chance to catch that one. I'm sorry. Now, so our limit is -1. That means that the left-handed derivative is -1. Now, what about the right hand? So if we plug in from the right, we get the same limit, but now we're talking about the limit as x approaches 2 from the right of absolute value of x minus 2 over x minus 2. So we're talking about a number bigger than 2. So 3. 3 minus 2 is 1. Absolute value of 1 over 1 is +1. So we've got 1 is -1, 1 is +1. They are not equal. That means the limit doesn't exist. Therefore, not differentiable. Now, what this means is only at that point, x equals 2, does it not have differentiability. All the rest of them we're good with. So this is going to leave us to define differentiability here. Differentiability implies continuity. This is very important. If f is differentiable at x equals c, then it has to be continuous. No ifs, ands, or buts. If you can differentiate it, it is continuous. However, it is possible for a function to be continuous and not be differentiable. And this is going to happen only at places with sharp turns, where you've got a point. Now, if you've got just a curve, it doesn't matter how steep the curve is, you're fine. But the second you have a point, if you have a peak, that is non-differentiable, okay? So if you have any questions about differentiability and continuity, please just shoot me a reminder or ask a question in class.